Thank you very much for the kind introduction. Thank you very much for this opportunity to give you the talk about universality in the free body systems of ultra-cold hybrid ion atom systems. I'm a bit free in my use of the word universality. What we mean by that is maybe not something that you're very much used to. I will explain it later in the talk, but we are actually just describing the universal properties of the model interaction that we're using, and that's how we use the word universality. But it is a more broader range than maybe the resonant free body bound states that you heard about, and maybe it may be a bit different from what you know about universality. But still, we are interested in calculating the free body recombination rates, which explain the dynamics of forming molecules in ion atom systems. We know that, you heard from Agata on Wednesday about the barium ion trapped in ultracold gas of spin polarized lithium, where certain Feshbach resonances were observed and were predicted, and certain ion losses connected to these Feshbach resonances were observed, but some of them were predicted for the PED wave collisions, not really observed, and also there were also ion losses that were observed but were not really predicted by theory. So the hypothesis is that maybe including the spin-orbit interaction would kind of mix the rotational motion of the species involved, and then without this including this in the model, that's why we don't see certain losses, or we don't confirm certain losses. Okay, but also we do see certain ion losses that may be connected to other types of resonances in the system. So maybe there are shape resonances which account for higher rates of combination into channels where the molecule that is forming is the lithium-2, not the barium lithium plus, because we know that when the molecule is forming, this binding energy is released into the kinetic energy of the species involved in the process. So we want to calculate these free body recombination rates and have an intrinsic, let's say, to have an insight on the rates of these reactions, these collisions, and with regards to the outcomes, right? And also, just the fact that we know what these rates are would maybe allow us to mitigate certain losses and produce more stable samples from the experimental point of view. So with this slide, I hope I kind of convinced you that we are very much interested in the free body physics. Just a side note here that we know that when we predict these Feshbach resonances with short ranges of interaction, we propose and create this rest state that after a long time of interaction, after a long time of interacting with each other, these species can form a molecule. So that was actually even confirmed in the experiment, because they measured the dependence of the rates of ion losses with regards to the density of atoms, and that's how we know that before certain times we only produce a rest state and facilitate the sympathetic cooling of the molecule involved. But then if we wait long enough, then we have these free body processes. I'm very grateful for Mian to actually having introduced this this physics already, because it would be easier for me to talk about it. As it was mentioned, we actually want to solve this problem, right? We want to diagonalize the Hamiltonian and obtain the energies, and then propagate the dynamics with our matrix propagation method or any other method, and then see these recombination rates, calculate them. So this is just a slide to show you that when we have free body molecule, when you have a free body system, right, where there are free atoms involved, or one ion, two atoms, then the initial, let's say, degrees of freedom are 9, because in the Cartesian coordinates we assign 9 degrees of freedom, and we would have to diagonalize a 9D Schrödinger equation, which would be kind of hard. But the Jacobi coordinates were already mentioned. They have the, let's say, the kind of physical picture of this mathematical concept is that, well, one of them is just connecting the two atoms involved, and the other Jacobi vector is simply the distance of the third atom from the center of mass of the two first atoms. And now we kind of factor out this center of mass motion from the problem, and now we only have a 6D problem. But we can go even further and actually factor out also the we can also factor out the orientation of the plane that the molecule is forming, right? Because with 3 points we have a defined plane, and by factoring out the rotation of this plane and only focusing on the intrinsic motion of the molecule, then we only are left with 3 degrees of freedom. So this problem now became a free body problem, a 3D problem, and the Schrödinger equation becomes dependent on the hyperradius, which is a scaling factor, and also on 2 other hyperangles, which are defining the geometry of the molecule. And then we this k squared operator from the last talk, it was called lambda squared, so it is the same operator. And yes, and by integrating out and diagonalizing the Hamiltonian on these couplings between different geometries, so by integrating these hyperangles, we are able to obtain the effective potentials, which are then calculated on a grid of hyperradial points. So we then are able to obtain the scattered functions. We can calculate the free-body bound states. But also we want to propagate the dynamics. We want to introduce the arithmetic propagation method and then calculate the free-body recombination rates. Okay, so as you see, this picture is, now we're in the free body world, right? And this picture is kind of becoming more and more difficult, even for a simple barium lithium system. So we see that we have these effective potentials, right? Which in the 2-body case would be the 2-body channels, and in the 3-body case, they are 3-body channels, where we have this, let's say these channels that we assign to scattered states and also to these bound states. So a 3-body combination would be a process where we have a scattering function that goes in at the collision energy here, and then through couplings, which are maybe increased or facilitated also by Feshbach resonances, but not only. These couplings can be facilitated by shape resonances, which we also want to investigate. As I mentioned, we want to differentiate between the two. So each of these avoidance crossings kind of accounts for the couplings in the effective potential matrix, which is calculated. And which is something I want to also talk about is that especially these kinds of processes where 2 couplings are involved are also of interest to us, because maybe in the case of 2-body calculations, we are not really able to to account for them, right? For the process where there are, let's say, 2 couplings involved. So as we see, this kind of picture is present here. One thing to note, I will talk about it in the future as well, is that the binding energy of the we can already kind of see, let's say, I would say this, that we can already kind of see this raw vibrational structure of this bound state of the molecules forming, even in the 3-body picture. So this is kind of neat at high hyperradius. So for now this. But now I want to also tell you that we need to keep in mind that there are different energy scales involved in the problem, and that the atom-atom, so the lithium 2-body collision channel is it's more deep and narrower. So the density of states is smaller compared to the barium lithium plus 2-body channel, and this means that while in our theory we can really converge and let's say we can be really sure and certain about the shapes and the energies of this bound state in the barium lithium plus problem, then kind of resolving the recombination rates into lithium 2 would be more problematic, because it is always the case that the theory firstly converges from the highest bound states, right? The most bound states. That's the energies that we are sure of the first, and then we need to increase the precision of our theory to kind of resolve the energies and the shapes of these states which are weakly bound. But these are the most interesting, because the probabilities of the combination rate into these states would be perhaps higher. And okay, so as I mentioned, our model of interactions is, this is what I mean by this universality, but actually what I mean is just the universal properties of the interaction model. And we use the Langevin potential, we use the Van der Waals potential for the 2-body interactions at a long range, but also at short range. It's just it's universal, right? These are the universal properties that we don't really care about the short range that much. Because we only need to resolve the scattering length of the system, and we know this experimentally. So it's okay. So and then by simply adjusting the parameter lambda, increasing it, we kind of making the wells more deep, and then we are able to, let's say, in our two-body model, we are able to support a certain number of states, and when we increase the lambda, we kind of, well, we support more two-body bound states in our model, and then we are able to resolve more free-body bound states in the free-body model. So that's what because the energy scales for ion atom is smaller, then we are able to more fastly, but in our process, it is more fast to converge with these bound states of two and free-body molecules which are comprised of ion atom. So here, this picture kind of represents that there's in our model when we change lambda, well, by changing the values of lambda, actually is making it smaller. That's what makes it the body potential, two-body potential deeper. So for that, not bigger but smaller. When we make the lambda smaller, then we see more, let's say, another weakly bound state, two-body bound state appearing, and this is connected. Let's say this is purely a theoretical picture connected to these more and more resonances in our theory, and with each of these poles, we kind of get better precision. Then we are able to converge the energies of the two-body weakly bound states. Okay, and kind of goes to show that even without the hyperfine structure, we can already see certain shape resonances in the baryon system. So this is actually kind of promising, but it was already mentioned that at high temperatures, these molecules will simply dissolve. So it's not really a physical. For now, it's still let's say, a theoretical model. But it's a promising, let's say, step for the future that we can already assign certain shape resonances in our theory. Right? We can actually solve this problem. And the conclusion would be that well, these universal properties of the system are very cost effective. By that I mean numerical cost. They are a tool for efficient explanation of this electronic structure in free-body systems and the dynamics. In the future, we will implement the hyperfine structure to properly predict the ion losses with dependence on the external magnetic fields. And we will investigate more systems where the quantum regime was obtained, and then we will be able to see what are the rates of forming of certain ground states, because even in the 2021 there was this experimental paper that they actually measured the appearance of Ytterbium lithium plus ion, but we maybe want to know what is the ground state of this molecule, so that we or basically we want to know the rates of collisions and probably, well, let's say, probabilities of forming these certain quantum states in this system, and then we maybe want to explain the experimental results by that. And with this optimistic, let's say, outtake, I would like to thank you very much for your attention and ask you if you have any questions.
Thank you very much, Jacek. We have time for questions. Yes, please.
Thank you, very interesting. I just have a question. Did you also, with your calculations, can you also see Efimov states, or?
Well,
for the
I mean, we are interested in the system where kind of the background strapping link for lithium is small, right? And then no, we kind of only, but we can calculate.
You can calculate.
Obviously, yes, because I mean, well, not obviously, but let's say it is possible because we have the effective free-body potential. So when we calculate it, we can calculate the free-body bound state. So maybe this wasn't something that I talked about much, but thank you for the question. Yeah, we can do it, and especially in the regime where these scattering lengths are high, then that's what facilitates the appearance of these resonant free-body states. So yeah, we can do it. This is maybe important for certain experiments.
Thank you.
In the experiment, it seemed that it was very important to have to include the triplet pi state that comes. Mm-hmm. Yeah, and so would that be possible for you to do this? Right now, of course, you have a very simplistic model, I guess. Yeah, where you exclude a lot of degrees of freedom. I'm not sure how important it is to somehow model also this triplet pi state.
I would say this. No, it is possible, and I mean because that's kind of also the let's say one of the conclusions is that we are interested mainly. I mean, we can introduce multi-channels, well, let's say many two-body channels in our theory. We can do it. I would also comment that reducing the degrees of freedom does not make it simplistic. It's the failure of describing the energy of group-Einstein states. That's what makes it simplistic. And also, I would say we can do it, and because we also, let's say, our main, let's say, how do I put this? The main thing that facilitates the physics that we are describing are the scattering lengths, and that we know for the pi state as well. Are there any other questions? Do we have time? Hello? Yes.
Yeah, thank you for your talk. I was just wondering the last figure with the results that you shown. I mean, how did you get those three-body rates finally? I'm not sure that I got how you.
Okay, we do this parametric propagation. So when we go back to, let's say this picture, I don't want to put a lot of formulas for you to see, and so I would just say this because we have this already. We have the potentials, we have the scattering functions. Yeah. Then because well, let's say go back here. So we know the, let's say, the eigenvalues of the adiabatic Hamiltonian, right? So we know the eigenvalues which do not, let's say, do not feel these derivatives, but then we kind of include the derivatives in the model, and we see how it affects the scattering functions that we obtain, and that's how we can, well, let's say, see the dynamics.
So what I'm saying that you are doing quantum dynamics calculation. I mean, you propagate the Schrödinger equation.
Yes. We solve the hyperradial Schrödinger equation. Yeah, we do that. Yeah.
But then I'm kind of surprised that you can do that because for such a system there are very few channels actually. So did you make any kind of approximation to have not too many channels? I mean, if I compare to what situation for lithium 3, for instance, which is incredibly more crowded than the figure that you have. So I was wondering if
that's the thing. I mean, we want as many. Well, because the channels, the free body channels, the more of them there are, it is the effect of the more two-body bound states we resolve, and we want to resolve as many. That's a kind of what I talked about. Let's say. Here, right? That we want to let's say resolve and have a two-body interaction that supports as many two-body bound states as possible, and then we have all these channels. But even though we can't really resolve the dynamics into those weakly bound channels, but these are already converged, so we know this physics is already known. Let's say here up here, so we can do it. Yeah.
Okay.
Yeah. So that's the limitation of our universal model. That is a cost-effective model, efficient tool for description, but there are limitations of numerical ones. Let's say. Thank you.
So if not, let's thank Jacek and all the speakers of this session, and we're off to lunch. I think we're supposed to